It's a great pleasure to have the co-founder of this famous seminar 21 years ago, because 2024 take away 2003. I drew Sills, who will talk once again in this seminar about interesting stuff concerning partitions. Go ahead, Drew.
All right. Thank you so much, Daron. So it's good to be back at Rutgers, if only virtually today. So I'm here in my office in Statesboro, Georgia Southern, where I've been on faculty for, this is my 18th year now, I think, and this is where I came after Daron was my postdoctoral advisor from 03 to 07. And so thank you, Daron, for that. All right,
We are
so
very happy to have you back.
One of the things, normally when I give a seminar talk, I use slides, but I remember Daron's, one of his many important opinions was entitled, Still Love That Old Time Blackboard Talk. And so we don't have blackboards at Georgia Southern anymore. They've taken them all away, but here I have a whiteboard in my office, so we're using that. All right, so and thank you all so much for coming. Before we get into the main point of the talk, okay, I just saw a sign flash on my screen. Host has spotlighted. Okay, I'll let you take care of the technical aspects. What I'm going to do here is low tech on the whiteboard. Before we get into the main topic of the talk, I need to define a few things on partitions. Not everybody, Daron warned me that it's a wide audience, so not everybody is an expert in partition theory. So just some very basic stuff. And so a partition of an integer n is just basically a way of writing n as a sum of positive integers where the order of the summands is not taken into account. And so, for instance, if we took the example n equals 7, the possible partitions there are 5, 4 plus 1, 3 plus 2, 3 plus 1 plus 1, 2 plus 2 plus 1, 2 and 3 ones, or a sum of 5 ones, where I haven't bothered putting the plus sign in, but you understand. And so the order that I write these down in doesn't matter, so we often impose a canonical order. We just say we're going to put the largest summand first and work our way down. If you do it in Maple, then it's the other way around. So you could also think of these things as multisets whose individual members sum to a particular number, n equals 5 in this case. So some notation around this. Another way that you let me just define this, that m sub I of a partition, and if we're talking about a generic partition, we often label it with the lowercase Greek letter lambda. So m sub I of some partition lambda is just the number of times I appears as a summand in lambda. And I'll stop using the word summand because I know I'm going to fall back into what we usually call it. Each summand is called a part of the partition. So the number of times I appears as a part. So another way you could represent a given partition is in terms of what we could call a multiplicity sequence. Since the order of the parts doesn't really matter, we could just keep track of the number of ones and the number of twos and the number of threes and so on and arrange that into a sequence. So for instance, the multiplicity sequence for this partition, we have 5 ones and then no twos, no threes, no fours, and so on. This partition, 2 and 3 ones, well, it's got 3 ones, it's got a 2, and then nothing of anything else. And of course, since all of these sums are finite, all but finitely many of the multiplicities have to be 0. And so on. In fact, if you really wanted to, you could be like Nathan Fine who actually defined partitions in his book. And here, let me just grab it over here. It's a highly recommended book, Basic Hypergeometric Series and Applications by Fine. I'll have more to say about this a little bit later in the talk. But when he talks about partitions, he actually means these objects over here, what I would call the multiplicity sequences. He doesn't use that terminology. He just says that's a partition of 5. Here's another partition of 5, and so on. Let's see, what other notation do I need? Oh yeah, the total number of parts in a partition. So we often write that as L of lambda. And so that's just the number of parts, and it's also called the length. So that's why we use the script L. So the length of this one is 5. The length of this partition is 2 because it's 2 parts, and so on. And the reason that it turns out we're going to need partitions for today's talk is the formulas I'm going to introduce are actually expressed as sums over partitions of a given number. So these are all partitions of n. So this is a notation that I don't know if it was introduced by George Andrews, but it's certainly used in his classic book on the theory of partitions. It's if you're writing it in LaTeX, it's \v dash. So like meaning vertical, and then there's a dash attached to it. And this means that lambda is a partition of n. So here, all of these are different partitions of 5. So what we're going to need is actually, so summing, instead of over, the positive integers or some subset of that, the index of the sum is actually going to be all partitions of n. And the first time that I think this kind of summation appeared in the literature that I know of was in P.A. McMahon's, Major McMahon's work in whatever paper he published before putting it in his combinatorial analysis, volume 1 and volume 2. So that was the first time, I think. And then later on, sort of the next time that I saw sums over partitions coming up was actually in this book, the Nathan Fine book. So since I'm advertising it twice, I'll just mention that I think this book was actually started out as just a sort of an informal set of notes that Fine kept. They started writing it maybe in the 1940s. And then he was originally at the University of Pennsylvania. Then he moved to Penn State. George Andrews got to know him when he was a graduate student at Penn, and then took a job at Penn State in part because Fine had moved to Penn State in the meantime, some point in the first half of the 1960s. And I think it was George Andrews who really encouraged Fine to publish this monograph. And it finally came out.
Did you meet him ever? Did you meet Nathan Fine?
I didn't. He passed away in 1994. And I was at Penn State for the first time between 92 and 94. He was retired at that point. And so I never actually met him face to face, unfortunately.
Well, I was lucky to have met him once in a conference. Yeah. It was very nice. Yeah.
Okay.
Yeah, I met him. Yeah, I remember him fondly.
Very good. Okay, so one other thing I should mention is one of the things we often like to do is when we have combinatorial objects is count how many there are. So we use the notation P of n to denote the total number of partitions of n. So for example, there are 7 partitions of 5. If I didn't miss any when I was writing them down, 1, 2, 3, 4, 5, 6, 7. Okay, got them all. So we would write P of 5 is equal to 7. All right, so that's the. Oh yeah, and so that I don't know if I just said this, so I'm sorry if I'm repeating myself, but I interrupted myself with my talk about Fine. So after McMahon, the next instance of partitions, sums over partitions of n that I'm aware of in the literature is in Fine's work. And recently, it's come up just sort of naturally in work that I've done, in particular with Robert Schneider at Michigan Tech. And what I want to present to you today is part of a larger project that I'm collaborating with with Robert and also with a graduate student at Michigan Tech, Hunter Waldron. All right, so I'm gonna make some space here. All right. So actually, the next thing I want to show you, now that I think of it, is I want to share my screen with you. This is from, I had already mentioned George Andrews' book on the theory of partitions, and I want to share with you an excerpt from that. So let me just get this right here. All right, so sort of the motivation for what we're going to do in this talk comes from chapter 6 of the Theory of Partitions, where basically it's a long chapter to use complex analysis to prove a result due to Meinardus in the 1950s. I think Meinardus. I think it was Gunther Meinardus, but I'm not sure of his first name. Anyway, and it's a very interesting result that inspired me to go in some other directions. And oh yeah, I just remembered. Let me stop to share. Sorry, there's one other thing I wanted to show you. So I had defined P of n as the number of partitions of n. One other important thing we should have is this result. So this is due to Euler in the 1740s, that you can write a generating function for the number of partitions of n for each n, and so put it into a power series, and it has this nice infinite product form. And I'll just take the opportunity to say that this is de Rhoon's seminar, so q is a formal variable. It's just a symbol, and so we don't want to hear anything about convergence or anything about q as a complex variable, and we don't need it.
Unfortunately, when you do asymptotics, you have to compromise.
You have to compromise. Yes. Well, I'm not going to be doing asymptotics. I'm just going to do some asymptotics as an inspiration for some other things. So, so I can still keep myself pure, I think. All right. So as de Rhoon correctly points out, with what they're actually doing here, and we have q has to be a complex variable to do the asymptotics. So we consider the starting point is a generalized infinite product here. If all of the a sub n's are equal to 1, then we can expand that as a power series, and the coefficients will be p of n, the number of partitions of n. So what Meinardus is considering is a more general situation. So there are many restricted partition generating functions where, for instance, the ANs are all 1s and 0s and that sort of thing. And we can consider some other things like other general combinatorial objects like plane partitions, where the a sub n is actually equal to n. It turns out McMahon showed that was the generating function for plane partitions. Now, to do the analysis, and again, we can see absolute q is less than 1 in that case, Meinardus had to restrict the a sub n's to non-negative real numbers. It turns out you can relax that, and the analysis can be extended so that you can actually prove the asymptotic result. Let's see, I'm trying to think. It was Heiko Todt in his 2011 PhD thesis that he wrote under George Andrews, where he showed that you could actually relax those and use any real number. So you could have some opposite of negative numbers to put some of those up in your infinite product, some of those factors up in the numerator, for instance. So anyway, the reason I wanted to show the book is because I just wanted to show here's the asymptotic formula. It relies on a lot of symbols here. So this D is really just a Oh, it's a Dirichlet series where you get the coefficients from the exponents and all. Anyway, that's ultimately the R of n is written as an asymptotic formula in terms of those A's, but the A's are kind of hidden in all the notation here. But anyway, if we go to the special case where you take all of the A sub n's, all those exponents to be 1, then you have the famous Hardy-Ramanujan asymptotic formula for P of n. And so it's just that this messy thing here just simplifies out to this. So that's the sort of the canonical example there. So the next thing...
the Rademacher extension with the full is an analog of this for the more general scenario of the full.
Yeah, so I'm glad you brought that up. It's so actually Hardy and Ramanujan did much more than this. This is just the kind of the first term of the asymptotic.
Yeah, the leading term. Then Rademacher did the full thing, right? Yeah.
Well, actually, and I don't think Hardy and Ramanujan get enough credit for this. They actually came up with an asymptotic exact formula where they were able to prove that for any n, the error term was less than 1 or less than 1/2 in absolute value. So all you had to do is take their full asymptotic expansion and round off to the nearest integer. Then it was Rademacher in, I think, fall of 1937, when he was preparing lecture for his graduate analytic number theory class at Penn, that was basically working it out, and he did it differently and wound up getting a somewhat different analysis that gave him an infinite series that converged exactly to P of n. That was similar in form, but a little bit different than Hardy and Ramanujan.
So anyway, an analog of this for the Meinard case, or Meinard only has a leading formula, leading term?
So yes, so the Meinardus is just for the leading term.
Yeah.
If for this more general infinite product with where the A's are not all 1, it gets much messier.
Okay.
And so there is no, as far as I know, there's no Rademacher type series version of this.
What's alpha in that expression?
I'm sorry, what's alpha? Oh yeah, that's a good question. So it's buried somewhere here. So remember that there's these exponents in this factorization. You take those exponents and you put them into a Dirichlet series. And the Dirichlet series converges for some positive real number greater than alpha. So,
okay, thank you. Yes.
This notation is rather thick here. All right, so the next thing I want to call your attention to, though, is that as one of the exercises at the end of the chapter, George has this student or whoever's doing the exercise show that the R of n's, that is to say the power series coefficients, satisfy a recurrence that depends ultimately only on those exponents. And so it's an interesting exercise. And this exercise actually appears also in David Bersoud's book, which I have a copy of here. And David also gives us the reverse problem. So you can write a recursion for the R's in terms of the A's or the A's in terms of the R's. And those are both lined up there. As Frank Garvan, who I invited to come to this talk, but he's overseeing an oral exam of one of his students now. And actually, George is also on a Zoom call for that same oral exam right now. So Frank, when he, well over 20 years ago now, started his he wrote a Q-series package for Maple. And in that Q-series package, one of the very useful functions is what he calls prod make. And it starts off with, so let me write this in the general form. It starts off with with any power series that has a 1 as its constant term, and then figures out what these exponents have to be in this factorization. And so that's basically he uses the recurrence, I believe, and that's the sort of the inverse of the George Andrews exercise that I showed you there. And I know in particular, so I see Matthew's little window there. So Matthew Russell and Shashank Kanade made extensive use of that from of this prod make to find some of their wonderful Rogers Ramanujan type identities. That basically, if I understand correctly, the idea is you set up some partitions that have restrictions on it, some general difference conditions, and so on. And then you count up how many you have for each n for a certain, for small n up to a certain point. And then you count those up and those become your R of n. And then you use prod make and you see if you get a nice infinite product out of it, basically. And if the ANs form a discrete periodic function, then you have something that could generally be classified as a Rogers Ramanujan type identity. So I hope I didn't misspeak at all. Matthew can chime in if I said anything. No, I got the thumbs up. Okay. So anyway, so I got interested in this relationship here. And we already had an asymptotic formula thanks to Meinardus, an asymptotic for the R's in terms of the A's. And then thanks to George and David Pursued, we have recursions for R's in terms of the A's and A's in terms of the R's. So I began wondering about, well, could you write some sort of direct formula, or is that just too messy? And it turns out you actually can. But the key is that you have to write it as a sum over partitions. So hence the preamble to my talk. And so let me just show you what it looks like. So the easier one of the two is this R of n. In terms of the A's, we can write it as a sum over partitions, all partitions of n. And in the general term has factorials of the multiplicity. So these will be different for each partition. These are the multiplicity. I just didn't want to write out M1 of lambda. So these are all of lambda relative to whichever partition you're summing over. And I'm writing it as if it's as an infinite string here. But as we said previously, in order to be a partition, all but finitely many of the multiplicities have to be 0. So you've got infinitely many 0 factorials in there. So they just, you can eliminate those if you like. And then in the numerator, this is where the A's come in. You get A1 sub M1, A2 sub M2, and so on forever, where I'm using the rising factorial notation. So parentheses A sub M from the world of hypergeometric series just means A times A plus 1 times A plus 2 and so on until you have a total of M factors, all of them, one apart from the next one. And so where did this come from? I don't remember if I figured it out empirically at first and then looked for a proof, or if it just sort of fell in my lap. But I must have known, I'm forgetting the details of this, I'm sorry, that I could write it as a sum over partitions, because I was led to reading that particular section in Fine's book. And I have to say that I think Fine's book, people know about it in the field, but it's not as read as it really should be. And it's not really our fault, because Fine's writing style is very terse, and his notation is often somewhat idiosyncratic. So he uses common ideas that we use in the Q series and partition field, but he writes things often in kind of a funny way that's off-putting. So it's certainly, there's a learning curve to get used to knowing what he's talking about. And it sort of seems like he writes a line, another line, and that's trivial. And then 4 lines down, before you realize it, there's some very significant deep result you never would have guessed. Anyway, but it's still I advertise this book because it's really worth the effort. So since somehow and I don't remember the details, somehow I had reasoned that I could write it as a partition, sum of partitions over n's. So I thought, oh, I better look in Fine's book, and then I found that this actually
you use a multiplicity notation, and so it's 1 superscript m1, 2 superscript m2. You use a multiplicity notation, right?
yeah, because they're the multiplicities, the number of ones that appear in whatever partition you're summing over, and the number of twos, and so on. Yeah, so that's exactly what the m's are from the preamble.
Yeah.
And
okay, thank you.
You're welcome. So it turns out that this is it's not in Fine directly, but it's an immediate corollary of one of his results in whatever section, I think section 22 in his book. And so once, this corollary of Fine's work, showed up in my lap here, I just, I thought, well, let's try and, examine what this is trying to tell us. So the first thing to notice if you write 1 sub m in the hypergeometric notation, that's just 1 times 2 times 3 and so on up to m. So that's just m factorial. So if we take the canonical example where where we're talking about partitions and all of the ANs are 1s, then each of these all cancel, in other words. So we've got a 1 sub m, this is m1 factorial over m1 factorial, and m2 factorial over m2 factorial. And so that tells us that all we're doing is something very trivial in that case, because everything cancels here. You're just basically brute force counting, you're summing, there's p of n partitions of n, and you're just putting in a 1 each time. So this is Deron's esteemed co-author, the late great Herb Wilf, would call this like a non-formula. I think Herb's favorite example of this was that the cardinality of a set S is given as a sum x, x in the same. It's the same kind of thing. So
yeah, it's an answer, but not a very satisfying answer.
So yeah, so so in the case of this example, it's trivial. And in fact, if we define P sub S of n as to be the number of partitions of n restricted where the parts all have to appear in S, then this is just an indicator function if n is in S, and then it reduces to chi, or chi is just the indicator function, a characteristic function, whatever you want to call it. So all parts of lambda are in S. So it's a 1 or a 0. So that's also not very satisfying, because you're using all partitions of n, and in general there's a lot of those, and with either a 1 or a 0 of whether you want to count it or not. So if we're going to do something that's a little bit more interesting, we have to have our exponents in here counting something of interest, where you've got more, where the a and n's are not just 1s and 0s. So you need some bigger numbers in there. And let's see, I want to make sure I'm following the canonical time here. Yeah, because I want to save a little time to talk about the other direction, which is actually more interesting. So if I could just define the over partitions of n very quickly. So this is another combinatorial object that's related to partitions, but a little bit different. Here's the partitions of 3. With over partitions, any particular integer that appears as a part can be distinguished by having an overline or not any particular, the last occurrence of any of these. You could also think of it for if you're a partitioner, you can think of it as a two-colored partition where one of the colors, the parts are distinct. But here's the classical way. So the last appearance of 2 and 1 either can have a line over it or not. And here's the last occurrence of 1 either has a line over it or not. Anyway, so you get more of them. And so, for instance, there's 3 partitions of 3, but there's 8 over partitions of 3. Anyway, you can show with not too much difficulty. I'll let P bar of n denote the over partitions of n. That A of n is equal to 2 if n is odd, and 1 if n is even. That's what the generating function for over partitions will look like. And then I already got my crib notes here. If you work through that formula and just cancel the factorials, that's what the general summand looks like. And again, the m's are the multiplicities in the partitions that you're summing over. And so this is much more satisfying than the previous stuff that I showed you, because the over partitions are a bigger set. So you're using a smaller set to count a bigger set. And you could also say from this result you can deduce exactly how many over partitions of n there are that correspond to a given partition, and it's this number given in terms of the multiplicity of each partition. I'll mention, just because I don't want to run out of time, I'll mention just one more example, again bringing up the great P.A. McMahon. So he studied something called plane partitions, and I won't go into defining that due to lack of time, but if we let capital PL of n stand for the number of plane partitions of n, I got this notation from Wikipedia. I don't know if it's standard or not. Here, an, the exponents in the generating function, and this was McMahon was the one who discovered this, the a sub n just equals n. So in other words, you get 1 minus q to the 1 to the first power, 1 minus q squared to the second power, and so on, all multiplied together. So then the number of plane partitions of n, if you do a little work on the factorials, the formula that counts them gives you, in terms of binomial coefficients, m2 plus 1, choose 1, m3 plus, I think, 2, just checking, yeah, 2, choose 2, m4 plus 3, choose 3, and so on. And again, this isn't really an infinite product here, because all but finitely many of the multiplicities are 0, and so you've got infinitely many, of the form k choose k, so infinitely many ones in there. So that's kind of interesting. So so you can set up, I guess, an injection from partitions to all plane partitions, and you know how many there are that correspond. All right, so I wanted to say a word or two about, I walked off mic, I hope you can still hear me, the other direction. So again, let's just keep in mind what we've got going on here. Here's our sort of fairly general power series with unit coefficient. And this particular sort of what we might call a q-Factorization of it. What can we say about writing the a's, the exponents, in terms of the coefficients of the power series expansion? And so this is something that I was working on over the summer, and so it was Robert and I collaborate all the time, and we meet over Zoom, and he's been kind enough to host me at Michigan Tech several times already, and it's always such a pleasure to go there. That's such an excellent place. Great students, great faculty, and I hope I'll be able to visit there again soon. Anyway, be that as it may. So so I was trying to do some things empirically and not making great progress. And Robert suggested, okay, the key to thinking about this is to consider the logarithm of this first as sort of an intermediate step. That is going to unlock some things. So if I take the logarithm of this product, infinite product, then that itself has a power series expansion. And the coefficients of the power series expansion of the logarithm, and this is a natural log, will help unlock some things. Using, taking the derivative of both sides of this, you can show that n times b of n is the divisor sum, so sum over positive divisors of n of d a sub d. That's a fairly straightforward exercise. Then now we're in a situation where Möbius inversion implies or applies. So from Möbius we get NaN is equal to the divisor sum. Now we need the Möbius function in there from number theory. And this is dBd. But this is great now because I can divide both sides by n, and then I have the a sub n's now written in terms of the b's. So if I can write the b's in terms of the r's, which it turns out to be an easier problem than trying to write the a's directly in terms of the r's, then by extension, I've got the a's in terms of the r's. And Robert went a little bit further and showed me that there was a form for the b's as a partition sum where it was some rational number, and different for each partition, but in terms of and I hope you can see that. So this is the r's, that is to say the coefficients of the original power series raised to the powers of the multiplicities, the corresponding multiplicities, for whatever partition you happen to be summing over at that time. And this was a rational, and this is through some argument, this is some unknown rational number. Now I was blown away by this and I thought that's great, but I didn't realistically think we could get any further than this. And I remember communicating with George Andrews about this over the summer, and sometimes things just get too convoluted, and so you just kind of got to cut your losses. But I didn't give up, and it was actually when I was on the plane flying out to the George Andrews and Bruce Baird birthday conference, which Daron and I know other people in the audience, some of you were at State College, Pennsylvania, Penn State last summer. So I was on the plane and I didn't have access to the internet, but I had my laptop and I had Mathematica on it. So what I did was I just generated a lot of special cases. Daron, I wish I could say I came up with this brilliant ansatz, and somehow I just fed in the right data and it just spit out the right answer. But that's not what it was at all. I just generated a lot of symbolic data.
So it's very fitting. It's experimentalist. It's experimental.
It is. Yeah. This is one of the reasons why I wanted to talk about that in this.
Yeah.
But it was sort of haphazard experimental. So I generated a lot of data And then when I got to Penn State, the first night I was dining alone, and I was looking at data. And then I got back to the hotel, and then eventually, bam, it hit me what the form was of this rational number. And it's really quite beautiful. So the missing piece of the puzzle is -1 to the length of the partition -1, or it's an alternating sign, so length +1 or length -1, whichever you prefer. L length -1 factorial, and the denominator is once again what we've seen previously: m1 factorial, m2 factorial, and so on. And so this is the full formula. And so so Robert helped me set this up. I had already kind of recognized that there was a Möbius function like this involved and all that, but he gave me the details how to get it up modulo what these coefficients were. And then doing experimental math, just looking at lots of symbolic data, I was able to guess this formula. And I showed some people at the conference. I'm glad I can, just privately. I didn't do this in the talk, so I'm speaking about it publicly for the first time today. And it's, as I said, it's part of a bigger project where we're going to include this result and some other things. Robert, for instance, has a more
and Drew, this is a beautiful formula, but Frank Garvan's packet doesn't it quickly can find it? Can they find the AN quickly out of Rn numerically?
From a computational standpoint, yeah. I would say the best formula is probably what Frank has programmed, which is a recurrence. I mean, recurrence are, really efficient a lot of the time. So this was more just like a personal challenge. Like, what if I wanted to write it as a direct formula? I'm not claiming that.
It's beautiful, but probably useless. Yeah, it's beautiful.
It's possible. I mean, I haven't done any tests of that sort of thing. But so yeah, so Robert, I'll just preview. I'll let him talk about it sometimes. Has conjectured a possible generalization of Möbius inversion itself that is sort of related to some of the ideas here. And Hunter is working on, among other things, some Q analogs of some of the stuff that we're talking about here, like Q analogs at this level. Again, I'll let him speak about that at some point. We are following the axiom, and I will not go more than six additional minutes. But I did want to say that so I was able to guess this coefficient from numerical or from symbolic data, but I did also come up with I was able to come up with a rigorous proof for that as well. And let's see, just in the final few minutes, let me just share some related questions to all of the business. Excuse me?
Before you erase that, are you allowed to just pick any sequence of positive numbers Rn and there's always ANs that work?
Yeah. So this is like a factorization that that works anytime you have a unit coefficient. And I mean, and even that is not such of a limitation, is it? It's because if you have something, as long as you have a non-zero number as your unit, you can divide the whole series through by whatever your leading term is, and then put it in this form. And if you have a bunch of zeros in the beginning, then you can sort of shift this, and then you have it in terms of q, a shifted q to the n minus something, right? So yeah, it's quite general and quite interesting. I don't have time to discuss, but if you put in, instead of partitions of n here, you put in compositions of n, so then your R of n is 2 to the n minus 1, you do get a factorization. And the sequence actually appears in the OEIS. So let's see, I'm not going to erase the whole thing. I just want to put this. So if we let C of n denote the number of compositions of n, So what are compositions? Those are like ordered partitions where 2 plus 1 and 1 plus 2 count as a different object instead of the same object. So it's well known and not hard to prove. There's lots of ways to prove it, that the generating function is this. It's a nice rational function. The C of n is equal 2 to the n minus 1. So this is exponential, whereas partitions grow sub-exponentially. But there is a factorization in this form, what I'm calling, for lack of a better term, the Q product factorization. And so the exponents come out to be, in this case, if we rewrite this in this form, in this Q factorization form, 1, 1, 2, 3, 6, 9, 18, 30, 56, 99. And so I looked this up in Neil's database, so I'm glad you're here, Dr. Sloan. And it's there. And so it's sequence A05996. Is that too many digits? I don't know. It's something close to this. I may have a typo in my notes.
I'm glad it was helpful.
And anyway, the OEIS indicates that the AN are the Lie analog of the partition sequence. I'm not sure exactly what that means. It says, which gives the dimensions of the homogeneous polynomials with one generator in each degree, and there's several other interpretations. So this was news to me, so I thought that was worth mentioning. And so let's see, what time is it? I've got 2 minutes left. So anyway, I'll just very quickly say that this raises other questions. So for instance, so I won't try to write anything down, so just reading from my notes. So what conditions on the R of n would guarantee that the A sub n's are periodic? And hence, if you multiply by an appropriate power of q, you'd have a modular form. I don't know if this helps with such a question or not. Seems to me that would be a pretty hard question. But I just thought I'd throw it out there for anybody who's interested. We've already talked.
Hey, Drew, what's the last digit? Sorry, what's the last digit of that A number? A05996L, is it?
Oh, no, 6. I'm sorry. But is that...
Thank you.
Yeah, so that's six digits. So that's the right number of digits, right?
Yes. Yeah, that's the right digit.
Yes. Okay, so unless I wrote it down incorrectly, that's the correct sequence, and we can all be looking at going to OEIS right now. So we already mentioned that P of n, partitions of n, grows sub-exponentially, and the compositions grow exponentially. So there must be some dividing line. Maybe there's some condition on the ANs that if you meet that condition, it tells you whether you're going to be exponential or sub-exponential. No idea about that. No idea if this formula helps you get there. And I see it's 5:48, so we stop there, and there's no further questions on my part, but I'll open it up to any questions that you all have for me.
Thank you for a very nice whiteboard talk with a beautiful handwriting and beautiful, complicated, but very, very beautiful formulas. We have time for questions. Any questions for Drew? I have a quick question. This OIS sequence, you found a new interpretation to this sequence, A05996.
Yeah, I would say it was not listed there, I don't think, unless it was in some form that I didn't recognize.
So can you prove this equivalent? Can you find a projection or some relation between you?
I didn't try, but I guess that would be good.
Yeah, interesting.
But so somehow the Lie analog of partitions, whatever that exactly means, is related to counting composition. So that seemed kind of cool. Oh, also, since we're here in my office, I want to hold the screen up here. Daron visited Georgia Southern, my university, some years ago, and I still have the poster up for that. And here's from Daron's 60th birthday party. So every day that I'm in the office, I get to be with Daron.
Thank you. Good company with George.
Yes, so George is 2018, his 80th birthday, and this was when he visited Georgia Southern. Anyway, I think I saw someone put something in the chat. Oh, okay, that was a private message. Okay, Dave. Thanks.
No, not a private message, but I certainly was targeting it at you.
Okay. Oh yeah, you did send it out to everyone. Of any, I thought you were sending it specifically to me, but yes, to everyone else too. So just in case your chat is not open, if anyone is interested in or knows someone who might want to join us as at MTU, again, highly recommended university. They got wonderful stuff going on there. We need a chair. Meaning MTU needs a chair, and there's a link to the job ad at Math Jobs. So. Yes. So
we're going back to mathematics. Any questions to Drew about stuff?
Drew, I have a comment and a question. The comment is that the A059966 does mention briefly in the formula section that your values for A sub n here for the compositions are those values. So it does make that connection in the OEIS entry. And the question I have is, the formula that's at the top of that OEIS entry looks very much like your formula at the bottom of your whiteboard. Do you have a sense of why there's that similarity?
Yeah, so thank you, James. So what James is talking about is, in this particular case, you have the 1 over n, you have the sum, and you have, but this part here is much simpler. It simplifies in this case to 2 to the d minus 1. All of this stuff can be, and I think that's what you're looking at, right, James?
Yes, that's correct, Drew.
Yes, so it's certainly not immediately obvious to me why all of this turns out to be this for this particular sequence. But thank you for pointing out that some connection between compositions. So this is not brand new from me here, but I think it deserves further exploration. Thank you.
So we have to find a connection or Wama correspondence or some kind of direct. Yeah,
that'd be very nice.
More questions to Drew? Well, thanks so much for coming. The recording will be available in a few days, and hope to see some of you next week. Thank you very much. And Stoyan, please end this meeting. Thank you, Drew, again. Thank you.
Thank you so much.
Thanks for everybody.
Bye. Thanks for coming.
Thank you.